Welcome to today's video, in which we will explore the successor to the previously presented 3D printed Micro-Manipulator. Unlike the first device, which is operated manually, the new design is a major step up as it allows fully programmable motion paths with higher resolution, faster speeds, and a larger working volume. It opens up a whole range of applications, some of them being demonstrated at the end of this video. The small ball joints used on both ends of the connection rods are a crucial part of the design. In contrast to flexures, they have a much larger range of motion while also being very stiff. The downside is that they have non-zero friction. To minimize this negative effect, the ball size is chosen to be very small compared to the length of the connecting rods. This large leverage combined with a suitable material choice keeps friction low. Another design choice enabling the presented construction is fixing the ball to the mounts and placing the joint socket onto the connection rods. Because the parallel kinematic design only produces forces in the direction of the rods, this orientation prevents the ball from jumping out of the socket under large joint angles. As you can see on the right, the force is always directed nicely through the center of the socket and the ball. The ball joints need to be preloaded to be able to transmit forces in both directions and not fall apart. For this, a small 1mm polyurethane rubber band is used. It can be sourced cheaply under the name Magic String. The material choice is important, and polyurethane can keep tension over a long time much better than your typical O-ring or silicone rubber bands. Each ball joint is preloaded individually and symmetrically. In theory, one could preload all 4 ball joints of an arm with a single rubber band. This was indeed what I tried first. However, it is extremely unstable, and the entire structure collapses rapidly as soon as one joint is overloaded and snaps out of its socket. The new design shown here does not suffer from this problem, and the joints readjust themselves nicely when pulled apart. If you haven't tried building such a device without this improvement, you might never fully appreciate how much of a difference this makes. When it comes to precision motion control, low-cost stepper motors aren't usually the first choice, yet these simple motors are more capable than they might seem when driven correctly. Using a high-resolution PWM signal for the winding current, steps of around 5 arc seconds are achievable in open-loop operation. That's equivalent to around 2,500 times micro-stepping. From a mechanical point of view, most stepper motors use ball bearings preloaded by a spring mechanism. While preload is effective at eliminating play, standard ball bearings are not ideal for high-precision applications. For now, we will use them as is, keeping in mind that they may be a potential source of error. When examining the interior of a stepper motor, it becomes evident that the stator contains a significant amount of iron. Since iron exhibits hysteresis under changing magnetization, the magnetic field inside the motor depends not only on the current flowing through the coils, but also on the material's previous magnetization state. Together with the residual friction in the bearings and ball joints, this makes it difficult to position the motor accurately without closed-loop control. For closed-loop control of the stepper motors, a precise rotation sensor is required to report the rotor angle back to the microcontroller. The feedback system of the Micro-Manipulator is based on an MT6835 magnetic encoder, which is quite affordable and offers an impressive resolution of 21 bits, providing over 2 million counts per revolution on paper. Due to noise, some of that resolution is lost, and about 100,000 counts per revolution can be measured reliably. These devices are intended to be used by attaching a diametrically magnetized magnet to the motor shaft and positioning the IC behind it, allowing it to detect the orientation of the magnetic field and, consequently, the position of the motor shaft. However, for our resolution requirements, 100,000 pulses per revolution are not enough and would give us a step size of about 1 micrometer. Pondering over different ways of increasing the encoder resolution using gears, friction drives, and cables, all of which would add additional complexity and problems with bearings, backlash, or size, I settled on a magnetic gearing approach with no additional moving parts. This approach is implemented by attaching bar magnets with alternating polarity onto the rotor in an arc shape and positioning the sensor tangentially and with a well-defined vertical offset. As described, low-cost magnetic encoders are designed to sense a rotating magnetic field. So, why does this work with a linear magnet array? To answer this question, it is best to look at a small simulation of the magnetic field lines. Here you see the simulated 3D scene. The following plots will visualize the results in a 2D cross-section, as indicated by the gray rectangle. In this visualization, you can see that above and below the magnets, there is a region where the field lines form regular loops. Further away, the magnetic field loosens this structure and gets smoother and more uniform. When zooming in and looking only at the direction of the magnetic field, an interesting pattern is revealed. What's noteworthy about this pattern is that, along horizontal paths, the local magnetic field orientation rotates smoothly and uniformly, so from the perspective of an encoder chip moving along the magnet array, the field looks like a rotating magnetic field. Exactly what we want. Also note that this behavior remains relatively consistent in the vertical direction, making it easier to position the encoder correctly. When examining the magnetic field angle along 3 horizontal lines at different heights, we can see that the linearity is not perfect, but quite good. In practice, variations in magnetization and manufacturing tolerances require calibration of the encoder response across the working range. This topic will be addressed later in the firmware chapter. With the given configuration, the encoder detects a complete field rotation every 2 magnets, effectively increasing the overall resolution by a factor of 30. The angle is unwrapped in software to provide a continuous signal as the rotor rotates through its operating range. The control electronics of the Micro-Manipulator is fairly simple, consisting primarily of a microcontroller and 3 dual H-bridge motor drivers. A small DC-DC converter supplies 5-volt power to all logic components. The encoder chips are connected via a shared SPI bus with 3 separate chip select lines. The board is intentionally designed to be double-sided and uses easy-to-solder through-hole components, making the project more accessible. Additionally, the bottom silk screen displays all pin numbers, which is especially helpful during firmware development. The microcontroller used is the RP2350, implemented here on a Raspberry Pi Pico 2 board. It is low cost, features a hardware floating point unit, 16 high-speed PWM generators, 12 of which are required for this project, and includes 2 CPU cores allowing the servo loops to run on a separate core. The choice of the motor drivers is more nuanced, as typical stepper motor drivers do not offer the required resolution or stability. Even those supporting up to 256 times microstepping fall short by a factor of 10. Additionally, many common H-bridge drivers, such as the DRV8833, rely on internal charge pumps and clocked logic circuitry, which can introduce output jitter, even when provided with highly precise input signals. I noticed this effect after observing random position fluctuations of the end effector under the microscope. The timing variations introduced by the internal clock, logic, and charge pump are clearly visible on the oscilloscope. In the capture shown, the yellow trace represents the input signal, while the blue trace shows the output of the motor driver. Fortunately, Toshiba's TB6612, another widely available low-cost H-bridge driver, does not suffer from this issue. It uses a combination of P-channel and N-channel MOSFETs, eliminating the need for a charge pump. The chip also contains only minimal unclocked logic and has demonstrated excellent output stability in real-world measurements. The firmware is written in C++ and aims to be simple and readable, while not compromising on features or performance. In this diagram, the main functional blocks can be seen. The servo loops for all 3 motors run on the second CPU core, providing a high update rate of 30 kHz to make the closed loop control fast and responsive. Everything else, including the math-intensive inverse kinematics, is calculated on the first core. The motion planning and execution process follows standard practice. When a motion command is received, 1 or more path segments are added to the command queue. This triggers look-ahead planning, which sets the start and end velocities of each segment to comply with acceleration constraints. Each path segment is then subdivided into linear joint space segments, and inverse kinematics is evaluated at their start and end points. In the timer interrupt function, these joint space segments are interpolated and executed one by one, with the resulting joint positions being passed to the servo loops. As mentioned earlier, the implemented encoder setup introduces certain nonlinearities and therefore requires calibration. For field-oriented control, the alignment between the electric field and the encoder angle must also be known. At present, this calibration is performed during the homing sequence. In the absence of a highly accurate absolute angle reference, the encoder is calibrated relative to the electric field. This method assumes the rotor follows the field perfectly, a condition that is not strictly true in practice, but is adequate for many applications that do not demand high absolute accuracy. The encoder provides input to the closed-loop motor controllers, which operate using a cascaded field-oriented control scheme. Given a target angle, a position controller determines a target velocity, which is then used by a velocity controller to generate a target torque. The torque command is converted into an electric field angle offset and added to the current field angle derived from the measured rotor position. Since the electronics omit current sensing for simplicity, the electric field angle is directly translated into coil voltages for the PWM outputs. The feedback signal for the velocity control loop is obtained from the derivative of the rotor position, calculated and low-pass filtered digitally on the microcontroller. Now let's take a look at the servo controller in action and compare it with classical open-loop control of the stepper motor. As you can see, closed-loop control not only enables highly precise positioning, but also makes the system significantly stiffer. The microcontroller firmware uses an inverse kinematic model to calculate the motor angles required to place the end effector at a desired position. In other words, it converts the target end effector pose into actuator angles. In the following animation, I want to explain how this inverse kinematic model works. We will focus on a single arm, as the procedure is identical for the other two. For a given target end effector pose, the position of one of the ball joints is determined using a fixed offset given by the CAD model. A coordinate system is then placed on the motor axis at the height of the corresponding ball joint on the actuator. On the XY plane, a circle is drawn representing all possible positions of the ball joint on the rotor side. Next, a sphere is centered at the position of the end effector's ball joint, with a radius equal to the length of the connecting rods. The two intersection points between this sphere and the circle on the rotor plane are then calculated, and the point with negative x coordinates is discarded. Now the angle between the other intersection point and the x-axis is computed. This angle gives us the required motor angle to move the end effector to the target position. Before discussing the results and applications, I would like to provide an overview of the device's build and assembly process. Feel free to skip ahead if you are not interested in this part. To demonstrate the capabilities and limitations of the device, we begin with a microscopy application. The test setup consists of the Micro-Manipulator and a camera microscope, using 395 nanometer illumination. The microscope is positioned above the end effector on which the sample is placed. The arrangement is somewhat makeshift, lacking a rigid base and relying heavily on 3D printed plastic components, so please keep that in mind. A die from an integrated circuit will provide a nice sample, as it contains many sub-micrometer structures and is interesting to look at. For all demonstrations, a small Python program is used that displays the live camera feed and provides a control panel for the device. It sends simple G-code commands and communicates via a serial interface with the electronics. The program can record waypoints that can then be replayed automatically. To visualize the motion more directly, it is also possible to track a point on the sample and draw its path to the screen, giving us an impression of the repeatability. More complex paths are best stored as a G-code file. As an example, a slice from the well-known Benchy is exported from a 3D printing slicer, scaled down by a factor of 1000 and loaded into the test program. The small offset you see is caused by the thermal drift of the plastics parts as they are heated by the camera and motors. We can push even further by lowering the speed and trace a Benchy that fits in a 20 micrometer envelope. By utilizing a more accurate tracking method of the microscope image with sub-pixel accuracy, we can measure the achievable resolution of the Micro-Manipulator. Here you can see the result for a 1 micrometer step size. Very nice. For 100 nanometer step size. And finally, for 50 nanometer step size. I am quite happy with these results, considering that the setup is not vibration isolated and made with a lot of 3D printed parts. A particularly useful application of the device is the automated alignment of optical components. In the following example, laser light is coupled into the core of an optical fiber, a process that requires precise 3D positioning with micrometer accuracy. In the shown setup, a camera microscope is used to monitor the fiber output, while the connected computer runs an optimization routine that adjusts the end effector's X, Y, and Z positions to maximize output brightness. Once the optimum is determined, the device can reliably return to the correct position even after large movements. There are also many other exciting use cases that could be explored in the future, so let me know which one is the most interesting for you. We've covered a lot in this video, and I appreciate you staying with me until the end. The presented prototype already performs well in many scenarios, but there is also room for improvement. The 3D printed parts could be replaced with machined metal components for better stability, while the ball joints can be upgraded to reduce friction by a factor of 5 to 10. Additionally, swapping the stepper motor bearings with ceramic ball bearings will enhance repeatability. Finally, it would be very exciting to scale the design up to a full 6 degree of freedom hexapod stage, a project I may pursue in the future. If you are interested in the continued development of this project and would like to support my goal of providing open-source solutions that everyone can use, learn from, and build upon, I invite you to subscribe to the channel and share your thoughts in the comments section.